Alright, we're back into section 3 of chapter 7. We were looking at imaginary numbers, I should say complex numbers, in polar form. And we were just looking at how to multiply and to divide these types of numbers that are in polar form, these complex numbers in polar form. In the previous video, we did an example of multiplication. Now we're going to do an example of division. And as you can see here, I've got a problem set up given z sub 1 is 18 CIS 75. Remember, CIS means 18 times the quantity of cosine 75 plus I sine 75. It's just an abbreviation. And z sub 2 is equal to 2 CIS 225. We're to find their quotient. Z sub 1 minus, or divided by z sub 2 would be, you take the moduli and divide the numerator 1 divided by the denominator 1 here, and then you subtract the arguments, the angles here, so that'd be, and first one minus the second one, 75 degrees minus 225 degrees, plus I sine of 75 degrees minus 225 degrees. Maybe I should use a bracket here, make it a little bit easier to distinguish. So this gives me 9, and then this would be, maybe I'll go with the bracket again here. The cosine of, this looks like, let's see, that would be what, negative 150? Plus I sine of negative 150. Now I want it in trig form, or in polar form here. So the only thing I'm going to do is I'm going to rewrite this by doing a coterminal angle to negative 150. I'm going to add 360 to this, and that would give me 210. So that would give me 9. And I'm going to write the cosine of 210 degrees plus I sine of 210 degrees. Again, traditionally, when we write it in polar form, the angle, the argument, is between 0 and 360, including 0 but not 360, or between 0 and 2 pi, including 0 but not 2 pi, and that's all they wanted. Now, if you wrote your answer using the abbreviation 9 CIS 210, that's fine as well. Don't forget your angle sign. Alright, now, in the previous video, we did a multiplication, and if you remember, we multiplied the moduli and we added the arguments. Well, with division, we divide the moduli, we subtract. But if you think about taking a complex number and raising it to a power, you're multiplying it times itself, times itself, times itself. So since you're multiplying it times itself, times itself, times itself, if you use the multiplication process that I showed you in the previous video, you would be multiplying the same modulus times itself, times itself, times itself, and you would be adding the same argument, the same angle, plus itself, plus itself, plus itself. So it was a French mathematician by the name of Abraham. Now I pronounce it Demoivre, but it's probably the wrong way to pronounce it. And they came up with Demoivre's theorem that says if z is equal to r times the quantity cosine theta plus I sine theta, polar form, it must be in polar form to use this, and n is a positive integer, then z to the n, which means you're taking all of this, and you're raising it to the nth power, can be done by taking the modulus, raising it to the nth power, and taking the arguments and multiplying by that power. Because again, if you're multiplying the modulus times itself, times itself, times itself, it's to a power. And if you're adding the argument to itself, to itself, to itself, you're finding that multiple. So we're going to do an example here. First one that's already given to us in polar form, and then we'll do an example where it's in rectangular form. And we're going to put our answer in this first one, and I guess in that one as well, in rectangular form. So if this is being raised to the third power, that means, hopefully I left myself enough space here, that would be 4 to the third CIS 3 times 70 degrees. So this is 64, 3 times 3, or 4 times 4 times 4, the cosine of 210 degrees plus I sine of 210 degrees. Now, since they want the, and that's polar form right there, since they want the answer in rectangular form, I'll convert this by evaluating the cosine of 210 and the sine of 210. Well, the cosine of 210 is negative square root 3 over 2, and the sine of 210 is negative a half, so I'll write this as minus 1/2 I. And then if I multiply through by 64, if I distribute, and I hope that you can still see this, the 2 will cancel with the 64, I'll get negative 32 square roots of 3, and then distributing minus 32i. And that would be this complex number raised to a power. Well, if you remember how to raise complex number in rectangular form to a power, it was the process of multiplying it times itself. You would be doing FOIL. And with an exponent of 3, that's not so bad doing FOIL. But if this exponent instead of 3 was, let's say, 300, well, doing it in rectangular form is for the birds. And here we go. Here, this is in rectangular form. If I wanted to and multiply this out, I could multiply negative 2 minus 2i times itself 4 times. So 4 factors of it. But I'm going to go ahead and do this using the Watt's theorem. But I have to convert negative 2 minus 2i into polar form. Now, instead of going through the actual process of determining what r is equal to the square root of a squared plus b squared, and figuring out what theta is, because these values are the same, this is a special, not taken to the 4th power, just the part, just the base. This would be negative 2, negative 2. Well, that would tell me that this is a 45, 45, 90. This is 45 degrees, so all of this is 225. And so this is going to be 2 square roots of 2, because it's a 45, 45, 90, and each one of these sides is 2. And that this is 45, so this would be 225. So I'm going to convert it this way. I'm going to write this as 2 square roots of 2, CIS 225, and that's what's being raised to the 4th power. If it's a special combination of A and B here, I can go ahead and just kind of common sense it using a 30, 60, 90 or 45, 45, 90. Or you can go through the steps and determine what r's, you get the same exact thing. So this is going to be 2 square roots of 2 to the 4th power. And then that's going to be, I'll just go ahead and write it out with the CIS, this is going to be 4 times 225. So 2 square roots of 2 to the 4th power, well 2 to the 4th power is 16, the square root of 2 to the 4th power is 4. 16 times 4, this is 64, CIS. Now 4 times 225 is 900. That's a little bit bigger than I want to deal with, so I'm going to subtract 360 twice. That would be 720, so that's going to give me 64 CIS 180 degrees. Well, that's not so bad to convert to rectangular form. That's a nice, easy to work with angle, so I'm going to write this as 64. The cosine of 180 degrees plus I sine of 180 degrees, 64, is equal to, let's see, the cosine of 180 degrees is negative 1. The sine of 180 degrees is 0. Of course, that's just 0, so my answer is negative 64. All right. Well, that tells me also, just kind of thinking about this backwards, if this is this number raised to the 4th power, then 64, if I took the 4th root of negative 64, I would get negative 2 minus 2i as one of them. Remember, when you're taking roots of numbers, there are going to be 2 square roots, your complex numbers, they're going to be 2 square roots, 3 cube roots, 4 fourth roots, 5 fifth roots, and so on. In fact, in general, there are n nth roots of a complex number. Now, we're going to use a variation of Demoivre's theorem to find roots as well, because taking a root of a number, taking a square root, is the same as raising it to the half power, which is what we're doing here with Demoivre's theorem. We're raising them to powers. Only in Demoivre's theorem we're using integers as the exponents. So in this case, if z is equal to r times the quantity cosine theta plus I sine theta, then for an integer n greater than or equal to 2, okay, then z has n distinct roots of the form. Now, what they mean by greater than or equal to 2, 2 square roots being the smallest, 3 cube roots, 4 fourth roots, 5 fifth roots, and so on. Now, the book's notation is w sub k. I'm not sure where the w comes from. I just went ahead and put it in there because that's how you'll see it if you look into the textbook. But this is First, you take the modulus, you raise it to the 1 over n power, or take the nth root of it, and then all of this stuff here with the k's, it's to get all the different roots, because you could have more than one root. You know, 2 square roots, 3 cube roots, 4 fourth roots, and so on. So we use this variation. I used to do it a little bit differently, but this is easy enough as long as you follow it. And this is for k equal to 0, 1, 2, 3, 4, all the way up to n minus 1. Because that would give us n nth roots. If you count the 0 as the first one, that would give you n nth roots. Now I know that's kind of weird looking, but I'll try to show you in an example if I can here. In fact, look at the example. Oh, actually this is fourth root. I thought I was doing fourth roots here. Find the cube roots of negative 64 over this set of complex numbers. And I already know one, negative 4, because negative 4 times negative 4 times negative 4 is equal to negative 64. So the other two, that one's real. The other two must be imaginary numbers. So we're going to rewrite these answers into the form of a plus bi. So first things first, I'm going to change negative 64 into polar form. Now negative 64 is the same as negative 64 plus 0y. So if you were going to graph this, you would be graphing way out here at negative 64, you'd be graphing this point. This distance here is 64, this angle here is 180. So in polar form, this is 64 CIS 180 degrees. Now if I'm going to raise, take the cube root of this, then I am going to take, notice the formula here, the cube root of r, which is 64, times the quantity, and I'm going to have to write, because there's going to be 3 of them, I'm going to have to write 3 of these expressions down, where this is 180 plus 2 pi, or 360k, where k is 0, so that'd be 360 times 0, all divided by n, which is 3, plus I sine of the same expression. Should put the degree signs down here so you can follow here. You can do this in radians as well. There's one. Here's the next one. (180 plus 360 degrees times 1 all over 3). Now I know you don't have to multiply it by 1 and write that in there, but I'm just to emphasize it there. I sine of 180 plus 360 degrees times 1 all over 3. And one more. You can see why I left so much space here. Cosine of 180 plus 360 degrees times 2. And this is our last one, because 2 would be the number smaller, the integer smaller, the whole number smaller than n by n by 1, so n is 3 there. I can just write this out and keep a thought here. 180 degrees plus 360 degrees times 2 all over 3. It's a little awkward. But there's no other way to do this. You cannot take, to my knowledge, you cannot take a cube root of an imaginary, or of a real number or a complex number, and get these roots in rectangular form. Maybe if you set up the equation, you probably could, because there is a cubic formula for solving cubic equations, but I'm not going that route. Alright, so let's see if we can figure this out. This is 4. Now 180 plus 360 times 0, this is just 0. So I have 60 degrees, so I have cosine of 60 degrees. And that's going to be the same plus I sine of 60 degrees. Coming back, this is 4. This is the cosine now. Now, this is 360 times 1 plus 180, that'd be 540 divided by 3 is 180. Plus I sine 180. Bet you this is going to be my negative 4. And we'll get to that here in a second. And now this one, this would be 4 Let's see, 360 times 2 is 720 plus 180 is 900. 900 divided by 3 is 300. So this is the cosine of 300 degrees plus I sine of 300 degrees. Okay, so let's see, the cosine of 60 degrees is 1/2. This, here, we'll write it as 4. The cosine of 60 degrees is 1/2. The sine of 60 degrees is the square root of 3 over 2. I'm going to put the I right there, and now I distribute, and I have 2 plus 2 square roots of 3 times I, or 2I square roots of 3. There's 1. Cosine of 180 degrees is -1. The sine of 180 degrees, I think I just did this, there he is 0. So this is -4, and I told you, and you probably already knew that -4 was one of the choices. And then last but not least, let's see, this is 4. The cosine of 300 degrees is 1/2. The sine of 300 degrees is negative square root of 3 over 2. Oops, negative. So let's make that a minus. And then I distribute through by the 4, and I'm going to get 2 minus 2I square roots of 3. And there is my third cube root. So there's interesting things that go on when you take the roots, the nth roots of a complex number, especially the graphs. If you were to graph these 3 points, if I'm not mistaken, and connect them, you would find that you would have an equilateral triangle, if I'm not mistaken. So there's all sorts of interesting things that can be done with roots of imaginary numbers, but that's a lot to remember. And the only way you're going to get better at it is by practice, practice, practice.